In this video, we will look at the black sheep scarves example in the textbook, the waiting line simulation. If you don't have your worksheet set up like this, you want to pause the video at this point and set up your worksheet. In the previous examples, we used static simulation models, models where each iteration of the model is independent of the other iterations. What we want to do now is set up a dynamic simulation model. In other words, the current state of this system is dependent on the performance of the previous states of the system. To do that, we will set up a clock that keeps a running time as we tick through the day, and we're going to want to see at any given time during the day how many people are in line, whether our service person is working or not, all of these things. So we're going to set that model up here. To accomplish this, the text gives us a flow chart of the process. It also uses narrative to explain how each step goes. You should work through that. One of the other things it does is it provides us with a 10 period example in table 16.4 that gives us check numbers. It provides us with arrival times. It provides us with service times, which are the two values that are generated at random in our model, that will allow us to build our model with these check values, make sure that it's working correctly, and then go and change the check values to the random values so we can move forward then with some sense that we haven't made a mathematical error in constructing our model. So the first thing we want to do is get these check values and put them into our model. We're going to do it for 10 customers, and those check values are provided on table 16.4. So you'll want to just go ahead and copy the arrival time and service time values in. Those are the two that are generated at random once we get the model set up. You can tell that it's arrival times and service times because we have inter-arrival times, uniform distribution, service times, normal distribution. So with these values, we'll go ahead and set up the calculations for our model, and then we'll come back when we're done and take care of the random portion of the model. So we'll build this static model here for 10 iterations. Now we have the flow chart and the narrative that explains what each of these steps are. And what we have is a couple of columns, arrival time and completion time, which are running clocks that are keeping track of what time each item arrives and what time each item was completed, so that we can do calculations to see if our service technician is available to work on the item when it gets there, or if the item has to wait in a queue before it's serviced. And it can be an item awaiting repair. It could be a person, a customer waiting at a counter or in line to be helped. So we'll go ahead and calculate our arrival time. And a characteristic of this type of model where the periods are dependent on each other is that the first customer or the first period serves as a baseline. Then the second customer or second period becomes the actual calculation that's copied down. So you normally have to complete the first two rows of a model like this. The first arrival time is simply going to be the arrival time that was calculated at random. That's when our first item arrives. Our service start time, it's the first item in the system, so we're going to start when it gets there. The waiting time is going to be the service start time when it started, which is either going to be equal to arrival time or larger than arrival time. So we want it first minus the arrival time. Now the time it takes to service the item is provided for us. We'll generate it at random later. And the completion time, we're just going to take our value here, our service start time. Here's what time it started. And we're going to add to that the time it took to provide the service. And that's going to tell us what time it was when the item was completed. So for example, it starts at 1.4, 140, whatever. It takes 2 hours and 30 minutes to complete. So it completes at 370. Well, we can't have 70 minutes, but you see what I mean. This is now the completion time in the system. And if you look at the table, you'll see that those values all match. So our calculations so far are correct. For our time in the system, we're just going to take our completion time, that's what time it's done, and we're going to subtract from that the arrival time, the time it showed up. So that would include any wait time, whatever. And that tells us that it was in the system 2.3 minutes, hours, whatever we're doing. And that, again, aligns with the table. So if you're following the narrative and working through, you can see that that's the case. Now, in order to calculate the arrival time for line 2, we take our inter-arrival time, so the time that is going to be generated at random, and we add it to the arrival time of the previous item. See, these things are arriving. They're just coming in. The first one arrived 1.4, and then we have the inter-arrival time value. The next one arrives 1.3 units later. So at 2.7, the next item arrives. These things are just coming in, independent of how quickly they're being serviced. Now, our service time, first of all, we have to check to see if the server is finished. So is our service technician available to service this new item? This item arrives at 2.7, but our service technician's not done until 3.7. So he's not finished. He's still working. So we have to check to see if our arrival time for our item is greater than the completion time. That means that our service technician is finished. He's already done when this new item arrives. So if that's the case, the service start time is the arrival time. Our service technician is free to start working on the item as soon as it gets it. He's not doing anything. Otherwise, he's not free to start working on this new item until he finishes the old item, in which case he's not finished yet with the previous item. So he needs to wait until he's completed with that item. So the service start time will be the completion time for the previous item. Close off my if statement, press enter. That looks right, matches what's in the text. Now we can go ahead and calculate the wait time, which is the difference between the service start time and the arrival time, in this case 1 unit. Again, the service time is 1.5. The completion time is the service start time plus the service time. So when did we start? We started at 3.7. How long did it take? It took 1.5. So now our clock is at 5.2. Our service technician is available at 5.2. Time in the system is the completion time minus the arrival time. That's how long it was in the system. Now that we have the second row completed, we can copy the second row down. The second row looks back to the first row. The second row takes into account the previous row, previous activity in its calculations to see if our service person is completed with the previous job so that he or she is available here. So we can just take this now and copy it down. We don't want to copy these columns, so we'll change them. And then these two and copy them down. They'll do the calculations. And you can take a look at the table 16.4 and see that our values match. So we have set our model up correctly. So now we're ready to go ahead and set up our inter-arrival times and our service times based on the distributions. So we know from the text that the smallest value on the inter-arrival time is 0, and the largest value is 5. It is a uniform distribution, so we can use the formula that we're given in the text, where we take our smallest value, so equals our smallest value, we'll need to make that absolute, and we add that to, then we take our largest value, we'll need to make that absolute, we subtract from it our smallest value, again absolute, and we multiply that times our random value. That gives us a random number. Then we have our service time, which follows a normal distribution with a mean of 2 and a standard deviation of 0.5. So we can take our service time and set that equal to norm.inv. The probability is random with a mean of 2. We need to make that absolute, and a standard deviation of 0.5. We need to make that absolute. That will give us our value. Now we want to take this inter-arrival time and copy it down to customer 2. We want to take our service time and copy it down to customer 2. Now to complete the model, the best thing to do is just to take all this extra stuff out because nothing's matching anymore. We'll go ahead, start with 2. They want 1,000 iterations of this. So I'll stay at the Home tab. I'll go over here to Fill. I'll fill a series. I want it to be in a column, step value of 1. I want it to stop at 1,000. Say OK. So we can check it in, down, 1,000. There we go. Now I can take my customer 2, which is the value that looks back to the previous period. It's the way all the other ones should look. Select it, double click the autofill node. It will fill down. I go down and take a look here. I started row 16. I go down to row 10, 15. So when I come up here to do my calculations, I'll do them here, remembering that I go to row 10, 15. So the number of people waiting in the system, I have a column here that says waiting time. If it's 0, then that means there was no one waiting in the system. So what I want to do is count the number of times that it's greater than 0. So I'm going to use my count if. I'm going to look at column E, beginning at row 16. going all the way to E1015. That's my range. I want greater than 0 in quotes. I'll close that off, and that will give me my value. I want to calculate the probability of waiting, which is going to be the number of people waiting in the system, the total number of customers. In this case, we did it to 1,000. You could type 1,000 in there. If you add more, you might have to use max or something. We'll just put 1,000 in here just to make it easy. The probability of waiting, the average time of waiting. So I'm going to use the average if function here because I don't want to include people who didn't wait in the average time of waiting. If you didn't wait, then you would just be weighing down the average time of waiting for people who actually did wait. The average time of waiting doesn't apply to you if you weren't waiting in line. It only applies to you if you were waiting. If you have to wait, on average, how long do you have to wait? So average if. I'll go back to my waiting time column, which is E16 to E1015. And again, I'll check to see if it's greater than 0. If it is, include it in the average. So if you had to wait, your average waiting time was 2.2 minutes, hours, whatever. The maximum waiting time, well, I think you can see how to do that. Let's calculate the max waiting time. E16 to E1015. Now we want to calculate the utilization of the quality inspector. In other words, what percentage of the day did our inspector spend working? And then, of course, the complement of that would be not working. In order to do that, we need to take a look at the total time that our inspector was inspecting, or the service time, and then our completion time. So I'm going to get the total service time, which is going to be equal to the sum of my service times. So service time is the amount of time it took our inspector to service each item as it came in. That's in column F, starting at 16 and going to F1015. Then the completion time, which I'll just take max, since it's a running total. I can go down and get the last one if I wanted. This is just easier, to G1015. That way it will get the last value. Since it's a running total, the last value will be the maximum value, but this is just a way for me to run down and get it. And then the utilization is the service time over the completion time. We can see that our inspector was working 77% of the time. The number of individuals or items waiting more than 1 minute to be inspected is simply, again, we'll use our COUNTIF function. We'll look at the waiting time E16 to E1015, but this time, instead of greater than 0, we'll say greater than 1. That way, spending more than 1 minute in the queue, close off the COUNTIF statement. 410 items waited longer than a minute, and the probability of waiting longer than a minute, again, the total number of items waiting longer than a minute over the number of possibilities for an item to wait longer than a minute, which is total customers here, 1,000, and we see that that's 0.47. That's how we complete the black sheep scarves exercise, where we're given check numbers, so we check and make sure our model is set up correctly. Then we insert the random values into our model, extend it out to the number of customers or periods or whatever, and then calculate our summary statistics.